Hi class, so I'm gonna making a video tutorial to give you some hints on number 1 assignments. So do it yourself. Okay, if you have any questions got stuck somewhere, then you can take a look at this one here. Okay, so I'm not gonna solve everything, but we'll give you enough hints at here. So the first question is to find the Thevenin equivalent with respect to terminal A and B at here. So essentially, you need to find the VTH. Okay, and also the RTH, right? Okay, between terminal A and B. So let's see, what do we do? First, let's find the RTH. To find RTH, what you need to do is you need to short the voltage source and open the current source. So if you do that, okay, and you'll end up with this circuit here, right? See, the voltage source is short and the current source is open now, and all you need to do is to find the equivalent resistance by looking at from this direction here, right? Okay, and of course it's fairly simple. You have two parallel resistor, okay, and then in series with these two, and then in parallel with this guy, and you can find RTH. Okay, so that's supposed to be 4k ohms. So the next one is to find VTH. To find a VTH, okay, I used node analysis. Okay, so I used nodal analysis. Okay. So you can try other approaches, but in nodal analysis, essentially to figure out how many nodes you have here. So in this case, I have 5 nodes, and you need to designate one node as the reference. So I'm going to designate node 5 as a reference. So it's like this is grounded here. And basically, you suppose you V1, V2, V3, V4, and V5, right? And if we can know V4, and that's essentially this VTH, right, which is equal to V4. So how do I find V1, V2, V3 then? Okay, V2 and V4. So we use nodal, essentially use KCL, the current, right, at each one node here. The summation of the current needs to be 0, right? Okay, so for the node 1, you don't have to. For node 1, it's just V1 equal to this voltage here, right? Yeah. For node 2, then you apply the KCL, right? For node 2, okay. If node 2 apply VCL is, you need to designate that positive here. Let's say I say V1, right, minus is higher than V2, so you have current flowing here. So V1 minus V2 divided by 3, so the current goes into here, right? Generally, you can call that as negative here. Okay, and just go into the node is negative. And if V3 is higher than V2, so that's the same thing going into there. Okay, and then V2 going out here. Okay, and that equal to 0. So then you have one equation here for this node. So similarly, you should try to get another one for node 3 and for node 4. So you have for node 3, node 4, you have 2 more equations. Okay, so solve all this equation all together here, and you should be able to get the value for the V4, okay, which is 8 volts. So there you go. That's the first question here. Okay, second question. It's a Wheatstone bridge question. The question asks you is to find current, okay, from node B to A. Okay, so basically this means the Wheatstone bridge that you have right now is a unbalanced bridge, right? And how do I know it's unbalanced? Basically, you look at the ratio between the 2 resistors here and the ratio of these 2 resistors here, and they are not the same, so it's not a balanced Wheatstone bridge, right? Okay. So how do I find ID then? So I give you some reference loops and the current direction in here. So if I look at this one here, what do I have here is basically I have 1, 2, 3, 4, and 5 unknowns, and I need 5 equations to solve these 5 unknowns. And I give you 3 reference loops set here. So I can construct 3 loop equations based on the 3 loops set here. I can also construct 2 equations based on the node B and node A using KCL. So that'll give us 5 equations here. Okay. So let's say, for example, for loop 1, okay, this loop right here, and use KVL. Okay, and we already have this current defined here. So KVL, if I go this direction, then this is negative I16, and it's positive 30 I3. And because we assume 0 internal resistance here, so this is basically plus 0 equal to 0. That's the loop 1. So similarly, you can get for loop 2, right? For loop 3, and you can get 3 equations here. So that's the 3 equations, right? But you do need 2 more here. Okay, let's try maybe to loop 3. So it's loop 3 is 75 plus I1 6 plus I2 12 equal to 0. Okay. So let's use node B in the A for KCL equation. Okay. So for node B, we have 3 currents. Okay. 1 goes in, 2 goes out. So node B, you have negative I1 plus I2 plus ID equal to 0, right? So that's going to be an A, you get another equation. So altogether 5 equations, you can solve for ID, right? You can solve for ID, okay? Yeah. Okay, so that's this equation here. So problem number 3, okay? This is also Wheatstone bridge, okay, and you are required to calculate the output, okay, with a relationship referencing to the input and also the resistance here. Okay. Now, in the class, I have used a little bit different bridge, but it's the same bridge, but in terms of difference, basically, how the orientation and how the numbering of the arm resistors, that's a different from this one here, right? Okay. Now you need to take a look at the difference between this one and that one. Okay. Now set up basically a sort of a connection. Okay. So look at the solutions of these two. How different are they? And if I give you maybe another different numberings, let's say maybe I call this R3, R4, R1, R2, right? And what will be the end results between EO, the voltage output, and the voltage input? So that's what I need you to establish at here. So for the time being, let's just see for this one here, right? For this one. So what's EO here, right? First for. So if I look at EO is the voltage drop from B to A, so that basically equal to VBA, right? So if I look at VBA, what's VBA? VBA, well, of course, is going to be voltage drop across R3 and voltage drop across R1. So that basically equal to VBC plus VCA, or equal to what? VBD plus VDA, right? Yeah. So this is simple here. So if I can find these two or these two, then I can find EO. Okay. So let's see, right? What's VBC and what's VCA? And VBC, right? VBC it here. Okay. That we can looking at is here's your input voltage. If I drop this input voltage over here, right? So what you're looking at is basically, if you look at this circuit here, okay, so that's a voltage divider basically. That's a divider. But in this case, what you're going to get is VCB, right? VCB here. So you can get VCB. It's a voltage divider. And what would that be? That's EI divided by summation of R3 plus R4 and multiplied by R3, right? That's VCB. But we need VBC, of course, that equal to negative, right? VBC equal to negative of this guy here, right? Equal to negative this, okay? And VCE equivalently, right? It's the voltage divider based on this branch at here, right? And we're looking at is EI divided by R1 plus R2 multiplied by R1, okay? So you substitute this into there, right? And you'll get VO, right? You get EO. Okay. Yeah. So So look at the yield, supposed to be this. So it's in a quite similar format as the one I gave you in my lecture notes. However, because the numbering of the resistors and also the structure, the orientation of the circuits, and you will see the difference there. Right? You will see the difference. Okay, so let's take a look at problem 4. This is a relatively long question in here. Still Wheatstone bridge, but for the time being, one of the arm, R1, is replaced with a thermometer. Okay, is a thermistor. The variation of the thermistor is based on this relationship right here. Okay. Initially, the bridge is balanced, so because all resistors are the same, 1000 ohm. Okay, that's basically the R0 value at here at this temperature. So the bridge is balanced at this temperature at here. Okay, so these circuits are the same circuit as really used in the lecture. Okay, as used in lecture. Okay, so your first question is to determine the normalized bridge output VO over VI. Okay, so basically, what's VO over VI, right? When the temperature, okay, equal to 400 degree. So this is very simple because when T equal to 400 degree, your resistance R1, right, will change. Basically, you need to write down the expression for VO and VI, or you need to derive that, right? Just like you derived on problem number 3. But you don't have to derive this one because we derived this in a lecture. Okay, so you can practice, but if you derive, you'll end up with this equation in here. Okay, look at this. Okay, so right now the R3, R4, and R2, they're fixed resistors, so then they're going to change. The only change variable is R1. And how does R1 change? It changes according to this function at here. So you can replace this R1 with that function and replace R2 to R4 with a nominal value R0. That's your fixed value. Then you can calculate VO based on that, right? And with the current temperature 400. Okay. Yeah. And don't forget that when you do the calculation, the T at here has to be converted into Kelvin, okay, in order to do the calculation here. Okay. So anyhow, so this is very simple. Based on the Excel, I give you a sheet, and this is approximately 498, I think 498. Okay, it's 498. Okay, so that's part A, and for part B, that's an Excel exercise. Okay, you need to practice this based on the template that I gave it to you for this part. All I need is to draw VO, okay, versus VO VI versus T, right? Yeah. So you'll get basically the response, okay, of this system at the different temperatures. Okay, yeah. You'll get something like this. Okay, you should get something like that. So that's good. And let's look at part C. So for part C, what it says is, so initially you're balanced, and then the question asks you to derive a delta VO, okay, to delta R1 relationship at here, right, and here. So this is a very similar derivation as we did in the class, but in the class we did the derivation with respect to the arm R2. So in this case, you are required to do it with respect to R1 arm, right? Okay. So here's your expression here. Here's your expression. So what we need to do is, right, and VO equal to that. Okay. So generally, basically, VO equal to this bunch VI. Okay. So now you have a small variation delta R1 based on the original R1. So then you will also have a small derivation, right? Deviation of delta VO because of that. And what do we do? Because any other resistors are not changing, so you need just to change that R1 to delta R1, right? And plus R2 at the bottom here, okay? At the top there, right? At the top of R2, so no change, okay? And R4 divided by R3 plus R4, right? Like this, okay? Over here. So then multiply by VI. So that's basically the expression because of the delta R1 change at here. And simplify these two, group these two terms together, right? Group them together, so you have R1 plus delta R1 plus R2 and R3 plus R4, and top is R2, R3, R4 minus R4, R1, delta R1 plus delta plus R2 and VI, right? Okay, so that's the expression here. Okay. Now, because initially all resistors are the same, so R1 equal to R2 equal to R3 equal to R4 equal to R. So you can replace all of them with R here, right? And then you can simplify based on that. You will get, right, a negative, okay, delta R1 over R0 divided by 4 plus 2 delta R1 over R0. Negative sign. Don't forget a negative. This is negative here. So which means if a positive change delta R1, you actually end up with a negative voltage drop at here, right? So because initially balance of V0 is 0, so that's how you get delta V0 equal to this, okay, equal to this. Okay, so that's good. Okay. So now the question here comes is, if delta V0 equal to 3 volts and Vi is 10, right? And what will be the delta R1? So we know R0, right, which is 10,000, which is 1,000. So we can solve for R1, so which is negative 750 if you solve that. Okay, so that means a change of temperature caused the resistance of the thermistor has a drop of a resistance of 750. Originally 1,000, and so your current value is 1,000 minus that 250 ohm for the thermistor, or the ARM1, right? ARM R1 resistance. Okay, yeah. And then based on this value, and you have your original temperature equation, okay, which is this. Okay, so R is known now, R0 you know, beta you know, T0 you know. You can solve for the T. So this way you can get the current temperature, right? The current temperature. Okay, so that's how you get temperature, which is 340.45 Kelvin, and you convert that to Celsius. Okay, yeah. And the last part, okay, is to calculate the loading errors. Okay, so loading error means you're supposed to use a voltmeter to measure this VO at here. Right, let's go back to the diagram here. So you're going to use a voltmeter to measure this VO at here. So if this voltmeter is not ideal, which means there's certain limited value of internal resistance, in this case it's Rin equal to 10,000 ohm. Okay, yeah. Now you will have this loading error, right? Yeah. So essentially what you're looking for is because the original Wheatstone bridge, you can equivalent that in using the Thevenin circuit. Okay, so this is your B and this is your D. Let's see, right? So this is your Thevenin VTH and RTH. Now VTH is basically your output voltage VO, and RTH is the equivalent output resistance between B and the D terminals. So how do I get RTH? Right, just like the first question you practiced, you need to short the voltage source to obtain the equivalent resistance between B and D. So basically just short here. So basically you're gonna have a short right over here. Okay, short here. So you're looking at basically a circuit, right? So you're looking for the equivalent resistance between the 2 points here, and you have 4 resistors here, right? And in the class I mentioned this is what. So basically these two are in parallel, and then in series with these two in parallel, right? And you can calculate RTH. Right? Okay, so this way you can calculate your RTH. I think I call it RB. Okay, and that equal to R1, R2. Okay, you can calculate that. Now we connect the voltmeter over here, so which means I will have this RIN internal resistance of the voltmeter at here, and you're looking for the voltage across this here, right? Across here. If this is infinite, then that's basically what you're looking at is this. But if this is not infinite, right, you will have a slight difference from VO. Okay, so of course right now this is your measured value, right? This is your measured, okay, or you call that VO measured here. So the VO measured is the voltage drop, okay, across the RIN. Okay, so voltage drop across and this is VO true value, okay, which is here, the 3 watts, and divided by what? RB plus RIN, right? RB plus and then RIN, right? So that's your measure value. Yeah, the difference between this and that will give you the loading error. Okay, so in this case, your loading error, right, is fairly straightforward now. Okay, so you end up with V loading, according to the definition, right, is a true value minus the measured and divided by the true value. Okay, so just calculate that. It's approximately 6.67, and I think if you get 6.54, it's also right. Okay, there's some approximation errors there, but either way, it'll be okay. Okay, yeah, because some students use the formula that I derived in the lecture to calculate the loading error. Okay, so in the lecture, the E loading is simply just RB or RTH. Okay. Divided by RTH plus RIN. Okay, that's the same thing. So you get this, you get 6.454%. Okay. Okay, so this is the number 4 question. Number 5 question is a sort of a instrumentation type of question. So you're giving a sensor, and you're giving a digital input port, and you're supposed to connect the two things together, right? And we say this is a PNP type of sensor, so which is basically what we call the sourcing sensor. So how do I connect this sourcing with the digital input port? Why is it called sourcing first of all? Sourcing is, you look at this transistor here, that's a PNP. Okay, so this is P junction here, and N and P junction like this. So when you have a small current flowing this way, and it'll turn on this transistor. And how does it? How could it be about a small current here? So you have a switch here, right? You have a switch. So if you have a switch, basically, okay, turns on the 2 terminal here, right? It'll allow current to go here. So you have small currents, and then this transistor will be on. If this is on, then the current will flow through here and it goes out here. So that's why it's sourcing. It's giving current out of this sensor. And what do you consider this? You consider this basically as a load. Okay, this is basically a load here. Okay, so you're sourcing, right? So you're trying to source the current into the load here. Okay, and first of all, of course, you connect to that because you need this 20 high power voltage. Okay, when the power switch is on, you have current flow. So current flows out of here. Okay, when it's on, and source it to this load, and of course you can connect to the negative side here, so you source to this positive for the load, right? And the load flows through the load and out the load, right? Out the load, and where does it go? Of course, it goes to the ground. and this ground here, right, also connect there. So that's basically give you a complete circuit here. Okay, yeah, so very straightforward. Problem 6. Problem 6 is AC circuits. Okay, now I realize we have a little bit different approaches in terms of solving a AC circuit, as you learned from 254, 255. Okay, but anyway, so let's stick to what I taught you in the lecture there, right? Okay, so we use the phasor concept. First, the question asks you to measure the current flow this capacitor using the ammeter or the true value without ammeter at here. So with the ammeter, basically you cause a little loading error here, right? Without ammeter, that's your true value, right? It's your true value. Okay, yeah. So the question here you got to be careful here is your input current is given as sine 1000 t. Okay. Now I need to write everything in the phasor format. Okay. So the phasor for the input, right? Phasor is a complex number. First of all, the phasor for the input here, right? It's in the class, right? We said it's cosine omega t. Okay, but this is sine omega t. So sine omega t equal to cosine, okay, omega t, so 1000 t, okay, and minus 90 degree, okay, minus 90 degree. So here's your phase here, basically. Here's the phase. So for anything, cosine omega t plus phi, right? And A here, okay? So the phasor is A angle phi. So in this case, that phasor IS, okay, use a capital there, is going to be A is 1, angle is negative pi over 2. So that's the phasor for the input current source here, okay? Yeah. And then what you need to do is you need to write down the phasor for each one of the component here. So let's solve maybe the first one when the switch is at the point P. Okay, when the point P. So when the switch is over here. Okay, so this is ZR, this is ZL, this is ZC. So ZR is basically 1 angle 0, and ZL is 500 millihenry. And that's anyway, you can use what would you call the standard there. Okay, so basically ZL is J omega L. Okay, so let's convert to standard. Omega is 1000 and L is 500 milli, right? So that's basically 10 to the power of negative 3. And what you get over here is ohms, right? It's ohms. So you can convert that to kilo ohms just to save your writing a little bit here. So that give you 0.5 J, 0.5 here, okay, 0.5 kilo ohm, okay, kilo ohm, okay, yeah. So that in terms of phasor, this is a complex number. So where are you? You are right here. So your angle phi equal to 90 degree. So that's basically 0.5 pi over 2 in a complex plane, okay. So that's the L, and ZC is 1 over G omega C. So you substitute C is 2 microfarad, and so G 1000 and 2 10 to the power 6. Okay, and that'll give you negative 0.5 J, okay, kilo ohm, which is 0.5 angle negative pi over 2. Okay, yeah, so now everything in phasor, okay, everything phasor. Okay, then the next thing is to solve the current, right? How do I solve that? It's basically now used Ohm's law, right? As if you use for regular resist type of circuits. Okay, so you have 2 impedance here, 1 impedance here, and they're in parallel, and we can get equivalent impedance of the 2 parallel multiplied by the current, so that'll give you the voltage of this network. Then you divide this guy as the current IC, right? Okay, yeah. So what do you get? So we get ZR plus ZR, ZL plus ZR, that's the one, and parallel with ZC, right? So this one equal to ZC, ZL, ZR plus ZRL plus ZR plus ZC. So then this one multiplied by IS, okay, is the voltage across ZC. And then you divide it by ZC, right? That's the current for IC, right? Yeah. So this acid is gone. Yeah, so you get ZL ZR over ZL ZR plus ZC IS. Okay. All of this one here are the phasors. So substitute phasors over here, 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 here. Okay. And do a complex calculation. So you will be able to get your ZC, which is 1.118 angle negative 63.4 degree, or it's 0.5 minus G. Okay. I have included some maple code in the tutorial and also in the lecture notes, so you are welcome to calculate and help verify that using your the software. Okay. So when you get this one here, now this is phasor, right? And we're, of course, in the time domain, where we have the ICT, basically this is your amplitude, and the sine omega t, sine is your yeah. So original is cosine. Your original is cosine omega t minus 90 degree, right? And then minus another angle here, this 0.4 degree. Okay, so that's basically your response of across the current across the capacitor. Okay, so 153.4 degree. There you go. That's your response here, right? Yeah, many times we call that basically steady state response for IC. Okay. You can do the similar thing for the part B. Okay, for part B, the difference is, right, the branch here, instead of just IC, right, this ZC, you have two more here. So if you call these two, let's see, ZIN, right? So you can calculate ZIN in here, right? And then this one in series is this, and then parallel with these two, and you can calculate the equivalent impedance, and multiply that will be voltage drop between these two terminals, and then divide by this portion in here, so that'll be your IC, right? Similar idea, but you need to calculate ZIN first. Okay. So we will get, that's what we call I true value, right? This is called, we call I measured value. Okay. So this I measured value you would be able to get is 1.015 negative 66 degree. Now, if I do a little comparison here, this is 1.118, this is 1.015, so the amplitude is a bit different. The phase is also a bit different, right? So that's what they call the loading error for AC circuits, right? The loading error for AC circuit. Okay. So and you're looking for percentage of magnitude error, right? So what do? So this one subtract this and divide it by this, right? So the error divided by 1.118, you get the percentage. Now phase lag, right? Phase lag beta is basically this one, right? Or this one, subtract difference between these two. That's about 1.6, right? That's 2.6 degree. Okay, 2.6 degree. And then that's your degree, but you're looking for the time lag here, time lag. So this one just divided by your omega, okay? 2.6 degree divided by 1000, okay, reading. Yeah, so you gotta be careful here. This is degree, this is reading, so I need to convert this one into reading, right? Okay, so now everything's good, and then it's approximately for 0.045 milliseconds. Okay. All right, so that's basically this assignments here. Okay, if you got questions, feel free to ask. Okay, so you still got a couple of days to go. Okay, thank you.